So good morning. First of all, I would like to thank the organizing for inviting me to give this seminar here. So my talk will be strictly related to Michaela's talk, although I will focus on a pure supergravity point of view. And in this seminar, I will discuss, review the construction of the n equal to 2 gauge supergravity, which was done in these works here, which described the low energy dynamics of superstring theory compactified on a class of Calabi-Yau, generalized Calabi-Yau manifolds. So let us quickly recall some facts about the relation between flux compactification and the gauge supergravity. The presence of fluxes in superstring M theory compactifications provide a mechanism for fixing moduli at the level of low energy theory. Okay. Thanks. At the level of the low energy theory, and moreover, already at the tree level, and moreover, in general, they will induce spontaneous supersymmetry breaking and possibly produce cosmological constant and other interesting properties of the vacuum. Now, as far as the relation between superstring M theory and supergravity is concerned, upon compactification on a Ricci flat internal manifold to 4 dimensions, in the absence of fluxes, the low energy dynamics of superstring M theory is captured by a 4-dimensional supergravity which is ungauged. Namely, it does not have local symmetries gauged by the vector fields. Moreover, the known superstring dualities are conjectured to be encoded in the global symmetries of these 4-dimensional supergravities or in extensions thereof. On the other hand, if we compactify superstring M theory on a more general internal manifold in the presence of fluxes, then the lowest lying modes, or more precisely a consistent truncation of them, are described by a 4-dimensional gauge supergravity, which this time is 4-dimensional supergravity, which this time is gauged. Namely, the reason for this is that the internal fluxes induce in the low energy theory minimal couplings which are naturally associated with local symmetries. Then, moreover, they will induce mass deformations and a scalar potential. Now, all these minimal couplings, and therefore all the local symmetries of the 4-dimensional theory can be encoded in a single geometrical object, which is the embedding tensor, which we will introduce later on, which by definition transforms covariantly with respect to the global symmetries of the ungauged theories, which are conjectured to encode the known superstring dualities. Moreover, in all instances of flux compactifications, the internal fluxes can be identified with the components of this embedding tensor. Therefore, the 4-dimensional gauge supergravity description of flux compactification may provide a valuable laboratory where to study the effect of the known string dualities on fluxes, thanks to this identification between fluxes and the embedding tensor. But now, let us consider, well, in the rest of the talk we will be mainly interested in a particular duality, which is mirror symmetry, which maps type 2A on a Calabi-Yau threefold into type 2B on the mirror dual. Mirror symmetry, the effect of this duality is basically to exchange even and odd homologies in the Calabi-Yau, and it can be viewed as a more sophisticated version of T-duality. Now, the presence of these, as a consequence of this duality, these two dual theories, they give rise in the low energy limit to two equivalent 4-dimensional n equal to 2 supergravities which are ungauged, as I previously said. Now, much effort has been recently devoted towards extending this mirror symmetry to the presence of fluxes. Now, it is useful to this respect to describe mirror symmetry as a particular T-duality along the T3 fiber inside the Calabi-Yau, as conjectured by Strominger, Yau, and Zaslow. Then, one would expect, as it is the case for ordinary T-duality, that Ramon-Ramon fluxes are mapped into Ramon-Ramon fluxes of a different order, and that Navier-Schwarz flux to be mapped into geometric fluxes or possibly non-geometric fluxes. Now, the presence, Michela has talked about geometric fluxes and non-geometric fluxes in her talk. Now, the presence of these fluxes, as Michela pointed out, suggests that perhaps the most correct framework where to formulate this problem is that of compactification of type 2 theories on manifolds with generalized geometry. Now, if mirror symmetry has to hold, and if this generalized compactification admits a four-dimensional supergravity description, then the gauge supergravities arising from the compactification of the two dual theories should coincide. Now, in what follows, I will review the construction, a proposal made in these works of this gauge supergravity, four-dimensional gauge supergravity, which is constructed from general symmetry requirements, and whose embedding tensor, namely the embedding tensor defining the local symmetries of the theory, captures all the relevant fluxes, namely all the fluxes involved in the game and which are mapped into one another by the effect of mirror symmetry. So they form a mirror covariant framework. Now let us recall some main facts about type 2 substring theories compactified on a Calabi-Yau threefold and their description in terms of supergravities, four-dimensional supergravity. Now, I guess we are all familiar with type 2 superstring theories in 10 dimensions. Their Navier-Schwarz sector coincide and consist in a graviton, a two-form, and a dilaton, while they differ in the Ramon sector, which consists in an axion, a two-form, and a four-form in type 2b theory, a one-form and a three-form in type 2a theory. These are the corresponding field strengths. Now, upon compactification on a Calabi-Yau threefold, these theories give rise in the low energy limit to an effective n equal to 2 supergravity, which is ungauged, and whose bosonic sector consists in a graviton and a graviphoton sitting in the gravitational multiplet, then H2 vector fields and complex scalars sitting in H2 vector multiplets, and then 4H1 plus 4 real scalars sitting in H1 plus 1 hypermultiplets. Now, in type 2b theory, this number H1 coincides with the H11 of the internal torus, H2 with H21. The scalars Wi sitting in the vector multiplets describe the complex structure moduli of the Calabi-Yau. The scalars Za, which are H1, sitting in the hypermultiplet, describe the Kähler moduli of the Calabi-Yau. In type 2a theory, it is the other way around. H1 coincides with H21, H2 coincides with H11. The Kähler moduli sit in the vector multiplets, the complex structure moduli sit in the hypermultiplets. The axions which we have denoted by zeta, capital lambda, zeta tilde, lower lambda, and which are 2H1 plus 2, they originate from the Ramon 10-dimensional forms. Finally, the axion A is the scalar dual to the Kalb-Ramon field B mu in 4 dimensions, and the phi is the 4-dimensional dilaton. Now, in the scalar fields in this lower dimensional theory are described by a nonlinear sigma model, namely they are local parameters, local coordinates of a Riemannian scalar manifold, which has the structure of a product of a special Kähler manifold MSK2, which is spanned by the scalar fields in the vector multiplets, times a quaternionic Kähler manifold, which is spanned by the scalar fields in the hypermultiplets. Now, among these scalar fields, the H1 complex scalars Za here, they span a submanifold of the quaternionic Kähler manifold, okay, which is a special Kähler itself. So in this lower dimensional theory, we have basically two special Kähler manifolds, MSK2 and MSK1. Now, since mirror symmetry exchanges the role of even and odd homologies of the Calabi-Yau, it will interchange also the roles of these two special Kähler manifolds. Now, as a general feature of sigma models, the isometry group of the scalar manifold is a global symmetry group of the scalar action. Now, as far as the manifold MSK2 is concerned, it is an H2-dimensional complex manifold which is spatial scalar. This means that in particular it is scalar, and moreover that it is locally defined by, apart from a choice of H2 complex coordinate Wi, by a 2H2 plus 2-dimensional section of a holomorphic flat symplectic bundle defined on the manifold itself. Now, in terms of this section, the scalar potential has this symplectic invariant form, and moreover we can define a covariantly holomorphic section V2 in this way here. Now, this covariantly holomorphic section plays an important role in the construction of the Lagrangian because, as it is known, it fixes the couplings of the vector fields to the scalar fields and the fermions. Then the vector Lagrangian has this general form here, where the H2 plus 1 times H2 plus 1 symmetric matrix N2 is defined in terms of V2 and its covariant derivatives. Its imaginary part plays the role of generalized coupling constants, you see here, but they are scalar field dependent. Its real part plays the role of generalized theta angle. Now, the isometry group of the manifold MSK2 can be promoted to a symmetry group of the field equations and the Bianchi identities of the n equal to 2 supergravity, provided its natural action, symplectic action on the section V2 is accompanied by a simultaneous corresponding action on the vector of electric field strengths and their magnetic dual, which is and this promotes this group to an electric magnetic duality symmetry of the field equations and Bianchi identities. Now, as far as the special scalar manifold MSK1 is concerned, which is a submanifold, the quaternionic scalar manifold, since it is special scalar, a flat symplectic bundle structure is defined on it, and moreover, we can define on it the same quantities which we have defined on the manifold MSK2, this time labeled by a subscript 1. Now, the scalar Lagrangian has this general expression here, where the first part describes the scalars in the vector multiplex, the second part describes the scalars, the hyperscalars ZA. Now, an interesting property is that the isometry group of the manifold MSK1 acts on the remaining quaternionic scalars, and in particular on the Ramon-Ramon axions, in a symplectic invariant, in a symplectic way. So we have used here a symplectic notation, and we have grouped the Ramon-Ramon axions inside a single symplectic vector ZA. The matrix Mn1 is a symplectic symmetric matrix built out of the imaginary part and the real part of the matrix N1, and it transforms under symplectic transformation like in this way. So now, as I previously said, the isometry group of the scalar manifold is a global symmetry of this action here. And now we will be interested in a particular subalgebra of the quaternionic isometry algebra, okay, whose generators, which I've denoted by TA, which are T lambda down, T lambda up, and Z, act on the Ramon-Ramon scalars and on the scalar A as translations respectively. In particular, they act in this way here. Now, it is easy to show that these generators close a Heisenberg algebra. So, we will be interested in a Heisenberg algebra of quaternionic isometries. Now, we want to gauge this theory. Namely, we want to introduce a local symmetry in these theories, which can reproduce the effect of internal fluxes on the low energy four-dimensional supergravity. Now, our proposal is to gauge an abelian group generated by an abelian subalgebra of the Heisenberg algebra. And we'll see that this is enough. We start from, we consider a generic abelian subalgebra of the Heisenberg algebra and promote it from global symmetry of the action to local symmetry of the action by deforming the action correspondingly. Now, the parameters of the gauge Lagrangian, namely the coupling constants, in our formulation are totally described by a single object, which is the embedding tensor here, which simply expresses the embedding of our gauge algebra inside the Heisenberg algebra. In other words, it expresses the gauge generators, which to be gauged by the vector fields, as linear combinations of the Heisenberg generators. Now the condition that G be abelian amounts to this symplectic invariant condition on the embedding tensor. Now it turns out that only a subset of the scalar fields parameterizing the Heisenberg algebra of isometries are charged with respect to this group G, to the gauge group. Now we want to implement this invariance under G, namely we want to deform the Lagrangian so as to make it locally invariant under the action of the chosen group. To this end, we replace ordinary derivatives as usual with covariant derivatives, and this amounts to this substitution on the axioms ZA and A. Then the gauge scalar action restricted to the quaternionic sector has this general form. However, the presence of minimal couplings, as it is generally the case, explicitly breaks supersymmetry. This is something we don't want, and we want to restore supersymmetry. And to this end, we need to further deform the action by adding additional terms to the supersymmetry transformation of the fermion fields, additional fermion mass terms in the Lagrangian, and finally, a non-trivial scalar potential, which is the most interesting part of the gauging procedure. Now, at this point, we need to generalize this construction. Why do we need to do so? Well, the gauging so far has involved an embedding tensor which has only electric components, namely it has just a lower index I. Now, this embedding tensor is manifestly covariant with respect to the symplectic structure on the manifold MSK1, the sp2h1 plus 2 structure, but it is not covariant, it is clearly not covariant with respect to the electric magnetic duality, which represents the symplectic structure on the other special Kähler manifold. Yes?
Yes, there was some work much earlier by DeWitt and Doria and Frey and so on, working out the general n equal 2 Lagrangian coupled to where you gauged isometry in the hypermultiplets.
Yeah.
Now, that wasn't complete in this?
It wasn't complete.
And what was missing there, or what?
The point is that they consider only they consider only, if you want, embedding tensors, which had, like here, electric components. Namely, the gaugings would explicitly break electric magnetic duality. This is the point. So the description of gaugings in terms of an embedding tensor is something which came out much later after year 2000, really. And that allows you to write, as I will show briefly, to write the equations of motion and Bianchi identities in a way which are manifestly invariant with respect to the electric magnetic duality, okay, provided we make this tensor consisting of coupling constants, transform accordingly. So this is the main point of this generalization, and we will use part of this. Now, since we want a supergravity, we want to formulate a gauge supergravity which has the same form for mirror dual theories, we need to express it in terms of an embedding tensor which is covariant with respect to both the symplectic structure defined on the two special Kähler manifolds, because mirror symmetry simply exchanges the role of these special Kähler manifolds. So, to this end, we need to add to the definition of the embedding tensor magnetic component, which makes it explicitly covariant with respect to the symplectic structure on both special Kähler manifolds. Now, the general formulation of gauge supergravity, which is of extended supergravity, which is invariant with respect to electric magnetic duality rotations, transformations, was done here in this work. However, for this particular problem, we shall follow a slightly different strategy. We will introduce this magnetic component via a minimal deformation, namely by simply dualizing only those Peccei-Quinn scalars which transform non-trivially under the gauge group. For the sake of simplicity, we will consider H2 smaller than H1 and the rank of the embedding tensor to be maximal. Then we decompose the Ramon-Ramon axioms into axioms Zi, defined in this way, on which the gauge group acts as translations, and in orthogonal complements Z hat, which are inert under the action of gauge group. Now, the axions Zi and the axion A, Nevers-Schwarz action A, can be all covered simultaneously by derivatives in the action. So they can be dualized into tensor fields. That's what we are going to do now. We can dualize the axion A into the Karp-Ramond field B mu nu, the axions Zi into corresponding antisymmetric tensors Bi, which are expressed in this way here. And then we introduce the magnetic charges by modifying the definition of the vector field strengths in this way, and correspondingly modify also the topological term in the Lagrangian, like this. Now, in order for this Lagrangian to be consistent, it has to be invariant with respect to both vector and vector gauge and tensor gauge transformations given by these formulas here. Now, this implies that, well, this is the case provided this generalized embedding tensor, namely its electric and magnetic components, satisfy these locality conditions. Now we wrote the scalar potential. Now the embedding tensor so far consists of a matrix components, which consists of these entries here, and a vector components, which is a symplectic vector, which we denote by lowercase theta. Now the scalar potential has this form here, where theta tilde is the matrix obtained by theta by raising and lowering the symplectic indices using the symplectic invariant matrix C. And the nice thing about this potential is that it is manifestly invariant with respect to the two symplectic structures on the two special Kähler manifolds. Now let us now make contact with a top-bottom approach, namely let us see to what extent these gauging, this embedding tensor reproduces the effects of internal fluxes. Let us consider type 2A compactified on a Calabi-Yau threefold in the presence of Ramond-Ramond fluxes, which has this general form. Omega I is a basis of harmonic 1-1 forms. Omega tilde I is a basis of harmonic 2-2 forms. Then we may also introduce Nevers-Schwarz and Nevers-Schwarz fluxes in this way, where alpha and beta, as usual, is a basis of harmonic 3 forms. And then we can also introduce geometric fluxes. This is done by deforming the Calabi-Yau cohomology, namely writing d alpha A as a linear combination of the omega tilde I, and also the omega I as a linear combination of the alpha A, through a matrix EIA, which encodes all the relevant geometric fluxes. Now, inspection of the minimal couplings deriving from this reduction tells us that our gauge supergravity describes the low energy limit of this compactification, provided the embedding tensor, the matrix component of the embedding tensor has just electric entries and coincides with EIA, and the vector component coincides precisely with the Ramond-Ramond fluxes. Moreover, interestingly enough, the closure condition on this deformation equation plus Bianchi identities imply those locality condition and the abelianity condition that we have separately, independently imposed on the embedding tensor, and which are a consequence of requiring consistency of the lower dimensional description. Now, a particular special case is this case in which the only geometric fluxes are described by these entries. These correspond to compactification on so-called half-flat manifolds, which were originally considered by several people, starting from these. And these correspond in the dual picture, in the mirror dual picture, to the electric component of the Nevers-Schwarz free-form flux. Now, we may think of adding also the magnetic component of this Nevers-Schwarz flux in the type 2b setting, but however, these do not correspond to any geometric flux in the dual type 2a setting, because they simply don't fit this scheme here of deformation. And as we shall see, they can be described as a deformation of a generalized cohomology defined on more general manifolds, which are manifolds with the SU3 times SU3 structures, which now I'm going to deal with. Now, and this, as Michela has anticipated in our talk, in this in this work here, recent work here, Grania, Lewis, and Waldron have discussed the compactification of type 2 superstring theory on manifolds with SU3 times SU3 structure. Now, these manifolds are characterized by 2b minus plus 2 odd forms alpha, 2b plus plus 2 even forms omega, which are forms of indefinite degree. On these forms, one defines a generalized exterior derivative, which acts differently with respect to ordinary exterior derivatives, in terms of which one defines generalized cohomology. Now, the idea is to introduce Nevers-Schwarz and Schwarz fluxes as well as geometric and non-geometric fluxes by deforming this generalized cohomology. Let's see how this works in type 2b. As usual, we will use the capital index I to label the four-dimensional vector fields, capital index lambda to label four-dimensional Ramon-Ramon axioms. Then we label the basis of odd and even cohomology correspondingly, and we deform the generalized cohomology simply by expressing d alpha r as a linear combination of omega a through a matrix which encodes all the relevant Nevers-Schwarz and geometric and non-geometric fluxes, and which has this general expression here. And moreover, we express d al omega a as the transpose of the tilde of this matrix times alpha r. Now, it turns out that our gauge supergravity describes a consistent truncation of the low energy, the lowest lying modes of this compactification, provided the matrix component of the embedding tensor precisely coincides with this flux matrix, and the vector component precisely coincides with Ramon-Ramon fluxes. Now, in type 2a setting, the role of the indices I and lambda are interchanged. However, the equations describing the deformation of the generalized cohomology have precisely the same form, okay, but expressed in terms of a new flux matrix, which has this expression here. In this case, the matrix component of the embedding tensor coincides with the transpose of the tilde of this flux matrix. Then, integrability with respect to this generalized exterior derivative implies the locality condition and the abelianity condition, which we have derived as consistency condition of our low energy gauge theory. Now, finally, if type 2a compactified on this more general manifold Y is equivalent to type 2b compactified on the mirror dual, which is roughly obtained by Y by interchanging even and odd cohomologies, then what should happen is that the corresponding low energy gauge supergravity has to coincide. This amounts to saying that the corresponding embedding tensor have to coincide. Now, this implies that the effect of mirror symmetry is to map the flux matrix Q into the transpose of the tilde. Now, the scalar potential, which we previously flashed, if expressed in terms of the flux quantities, is not invariant under this transformation because of the first line. However, if we extremize it with respect to Ramon-Ramon fields, we see that the first line it becomes 0, okay, and the last two lines, they can be written in a manifest n equal to 1 form in terms of this superpotential, and this which was originally proposed by Berglund and Meyer, and this potential is manifestly invariant under mirror symmetry. To conclude, we have proposed a gauge n equal to 2 supergravity, which describes the compactification of type 2 superstring theory on SU3 times SU3 structure manifold with general fluxes, and this is based on the gauging of an abelian subalgebra of the Heisenberg algebra, and all the geometric, non-geometric, and form fluxes are encoded in the corresponding embedding tensor, satisfying these quadratic symplectic invariant conditions. And they appear in the Lagrange in a mirror covariant way. Now, it would be interesting to find a more general characterization of the internal geometry, of the internal geometry, which can allow, as it happens for supergravities with higher supersymmetries, allows for non-abelian gaugings in the four-dimensional theory. Moreover, it would be interesting to understand what happens to the gauge supergravity if we take into account quantum corrections, namely to see if, as we expect to be the case, the presence of fluxes protect the gauge isometries from quantum corrections by means, for instance, of a mechanism which generalizes the mechanism described by Kashanian-Pur and Tomasiello in this paper of theirs. Thank you very much.
Questions?
Yeah, I couldn't tell from your talk. Do you actually have in your set of gaugings enough possibilities to characterize the most general abelian gauging of the n equals 2 supergravity you get from a Calabi-Yau? Or are there abelian gaugings that you don't capture this way?
Sorry, or?
All abelian gaugings.
Not really. Well, the condition that the gauging be abelian, well, this is a proposal for reproducing this general, for producing a gauge supergravity which accommodates all these fluxes and reproduce the right couplings. Now, the condition that this algebra, this gauging, be abelian, actually coincides in the microscopic description, in the description of the with the way, well, it's consistent with the way in which these fluxes have been introduced in this generalized compactification, namely as a deformation of the generalized homology. Indeed, the condition that the gauge group be abelian is a consequence of the integrability of these deformations.
But do you then think there are missing fluxes that would characterize the more general gaugings that you haven't found yet?
Well, this I don't know, of course. I mean, that would be interesting, really, to understand.
Yeah, I want to ask almost the same question as Shyam, but maybe it was exactly the same. But in the ordinary flux story, you can, depending on whether you do 2A, 2B, or Raymond, or NS, you can gauge any isometry of the hypermultiplet manifold with respect to give it graviphoton charge, or you can give any any abelian charge to the universal hypermultiplet. But supergravity allows much more than that. And so the question is whether you think by this kind of construction that much bigger space of abelian gaugings can be realized.
Of course, I mean you can, in principle, you can gauge any abelian subalgebra of the quaternionic isometries. This is something you can do by giving charges to the quaternionic fluxes.
But can you give a charge other than graviphoton charge?
Well, yes. I mean, the vectors which are involved in these gaugings are not just the graviphoton. I mean, they're all the vectors of the theory. But the important thing is that this subalgebra had to be a subalgebra. This algebra, abelian algebra, has to be a subalgebra of the Heisenberg algebra. This was important in order to reproduce the couplings.
Any other questions?
Yes.
So mirror symmetry is usually a statement about conformal field theory. But when we turn on these NS fluxes, we're generating a potential, so there isn't a conformally invariant string world sheet. So how are we supposed to think about mirror symmetry in that context?
In the context of conformal field theory, you mean this in the framework of string theory? You mean?
Well, conformal field theory, I guess, is the basis of our belief that there is mirror symmetry.
Yeah, yeah.
And but once we turn on fluxes, we generate a potential, so there is no conformally invariant world sheet.
Yeah, yeah, yeah.
So how do we understand mirror symmetry in that kind of context?
Well, that is a non-trivial question, actually. There are works in this direction, but I cannot give you a precise answer to this question.
Okay. Oh, one more question.
Well, just with regard to the previous question, I mean, there is a conformal field theory, at least a candidate one, obtained by letting the space expand with time according to the equations of motion. So you could try and analyze T-duality and mirror symmetry in that way.
All right. Okay, thanks.
Okay, so if there are no other questions, we thank the speaker again. So we reconvene at 3 o'clock.